Hi everyone and welcome back to PrepFusion. I am Anish and today we will start with the lecture 53 of our electrical machines subject. So today we will discuss about the remaining topics which were supposed to be discussed in the previous lecture, but the previous lecture was just 2.5 hours long. Actually it took me 4.5 more than that to record that. Okay, you guys don't understand what kind of effort it takes to record all these videos, make the content, right? Trust me. So today we will discuss about the remaining topics. We will discuss about different conditions of excitation, basically the V curve and inverted V curve, but that is very important. Also we will discuss about equivalent circuit of a synchronous motor and we will do the questions of assignments, right? Before that, before starting this, right, I just wanted to clarify a confusion between the torque angle, because I also previously may have messed up the torque angle, saying that the torque angle is the angle between the field mmf and the what do you say, field mmf and the armature mmf, right? Actually I was wrong. Actually I was wrong there. That is not the torque angle. So torque angle is always the angle between vt, angle between vt and ef. Torque angle is the angle between vt and ef. That's it. That is the end of the discussion. Now you might say, sir, previously you had said, sir, torque is proportional to fr, ff, or fa, ff, and the angle between f, sine of angle between fa and ff. Is this wrong? This is correct. Okay, but this is not the torque angle. Torque is proportional to this, right? Torque is proportional to this. Torque is also proportional to this. Fr, just the constant will change then. Ff, then the sine, sorry, this will be sine of angle between fr and ff. Okay, so this is also correct, but this is not the torque angle, right? Torque is proportional to sine of this angle and the multiplication of the mmfs, but this is not the torque angle. Just be careful. So torque angle is always the angle between the vt and ef. What is vt in terms of mmf? That is something else, right? I cannot write it, right? Vt will have some mmf that I am not able to represent. We are able to represent er. So what is er? So er, if you remember, so this was my synchronous generator. Then I had the armature reaction, right? XAR, JXAR, and then I had this ER here. Correct? If you remember, this was my EF, and after that again I have this RA plus JXS. Sorry, RA plus JXL, leakage reactance. Then after this I have this VT, right? So this VT also will, some MMF will correspond to this, but we are not interested. Generally we don't discuss about it. Okay, so mostly the torque angle is the angle between VT and EF. Very important. Why very important? Because this angle, right, is present in the power expression. Power P is equals to EF VT by XS sin delta. So this power, right, either in case of generator it is called as the power angle, in case of motor it is called as the torque angle. The names can interchange. Okay, don't get confused, the names can interchange. So just be careful regarding this. This is the called as the torque angle or the power angle. Okay, so I hope this thing is cleared regarding the torque angle and the power angle. Now let's come back to our topic, that is, if a generator is connected to a infinite bus, what will happen to the load current and power factor if I am changing the excitation? Okay, so few things we will have to keep in mind. First of all, it is an infinite bus. If it's an infinite bus, that means my Vt will be constant. So what conditions I will apply? Vt is constant. Vt is constant, and my what else? My Ia, sorry, not Ia, my frequency is constant. Vt and frequency is constant. Also, one more assumption we'll take. It is not like my XS, synchronous reactance, is also constant. It will not vary, obviously. Synchronous reactance will not vary. If frequency is constant, but basically my speed of the prime mover is constant. Now another approximation we will make, that now all these are constant. Now if I say if power is also constant, if power is also constant, that means what? If power is constant, that basically means that what is my power expression? Power is EF Vt by XS sine delta. Now one more thing I want to mention, that when will the power be maximum? If all of the other things are not varying, when will the power be maximum? So power P max will happen. This I think I have mentioned previously as well, at delta equals to 90 degree. When delta power angle is 90 degrees, power will be maximum because sine 90 is 1. Okay, that is clear. Now if I say power is constant, if I say Vt is constant, if I say Xs is constant, that means what can vary? My EF sine delta has to be constant. EF sine delta has to be constant. Why? Because this is constant, this is constant, this is constant. So if I take all this on the left hand side, that is a constant. So EF into sine delta must be constant. EF into sine delta must be constant. If my power is constant, what is the other expression for power? Other expression for power is Vt into Ia cos theta, that is equals to power, right? If this is constant, Vt is already constant, I know, right? Power is constant. So basically one more relation I can say, that my Ia cos theta also will be constant. I cos theta also will be constant. Okay, so all these will be constant. Which things will be constant? This is the first thing, Ia cos theta will be constant, and EF sine delta will be constant. Okay, so one thing you have to understand is, if I am increasing my excitation, that is if I am increasing my IF, that basically means what? In the previous lecture we discussed, that basically means I will increase my EF. So if I'm increasing my excitation, EF will increase, but the power angle delta will reduce if I say power is constant. And what happens if I increase excitation in case of a synchronous generator? Please remember what happens. If I'm increasing the excitation for a synchronous generator, that means the load is going from leading to lagging. The load is going from leading to lagging, correct? If I'm increasing my excitation. So load, initially, if let's say it was under excited, right? If it was under excited, then the load was leading. Okay, this we have previously discussed, right? Previous lecture, just revise once, previous lecture. So if I say initially it was very less excited, so under excited. Under excited means the load was what? Load for a generator load was leading, right? Then I came to nominal excitation. So in nominal excitation, what will be the power factor of the load? The power factor of the load will be unity power factor. And in overexcitation, what happens? In overexcitation, it will be lagging, correct? And one more thing that you must remember, because I'm increasing my excitation, I'm increasing my IF. So in all these cases, right, if let's say this is the EF1, this is the EF2, this is the EF3. EF3 greater than F2 greater than F1. Okay, so if I'm increasing the field current, obviously the excitation will only increase, it will not the voltage will only increase. Okay, so let's discuss about few graphs basically. So first one is the this Ia cos theta. So I have told you that my this Ia cos theta is constant. So if you notice one thing, cos theta, right? What is the range of cos theta? Cos theta, the range of cos theta actually is between 0 and 1, but it has special range. What kind of special range? So 0 and 1, if I say for the lagging case, right, another range it has. For leading case also, the cos theta can vary from 0 to 1. Correct? There can be two cases. There can be two cases over here. So if at first if I assume it to be a lagging load, if I assume it to be a lagging load, what will happen? Then the current, right, will be somewhere around here. Or let me assume initially a leading load. Okay, if I assume a leading load, current will be somewhere around here. Now if current is somewhere around here, okay, let me not do this. I actually want to do something else. Yeah, no, let us, I will discuss about the this power factor. Let me first, okay, where did you go? Yeah, let me first actually discuss about the first thing, right? This one EF sin delta is constant. Okay, so actually what is EF? What is the equation of EF? So EF, very simple, right? If I ignore the armature resistance, okay, neglect the armature resistance, EF will be equals to V plus J IA XS. EF will be equals to V plus IA XS. Okay, so yeah, that's it basically. So if I say IA is here, IA is somewhere around here, okay, IA is somewhere around here. So your if I say your IA J IA XS, right? So IA is here, so I have to add another plus 90 with this, right? So J IA XS will be plus 90, so it will be somewhere here, and your EF will be this. Correct? Now one thing you have to keep in mind, that we will make sure this condition is satisfied, that is EF sin delta is constant. That means this is the angle delta. So this is my EF. So this is EF cos delta. What will be EF sin delta? EF sin delta will be this. So basically this, right, EF sin delta will be constant. So this is, let's say, EF1, and this is this, let's say, delta 1. So let's say I am in a different load. If it's a different load, right? If it's a different load, that means okay, one more thing. Yeah, that means it has to actually follow a triangle. Basically, it has to follow a triangle. It should be here somewhere here. Actually, my drawing is not that good. Okay, it should be somewhere around here, because it should touch here. Okay, why it should touch here, I will explain. Because this length, right, is constant. That's why this length has to be constant. So it has to touch here. This triangle has to touch here no matter what. Okay, the delta 1 will be this. Now if I change the load, let's say if I am changing the load to here, okay, another theta, I am rotating this somewhere here. It does not matter whether it is leading or lagging, and load is somewhat this, and let me change the color. I2, okay. So let me keep it. So now what will be the new EF2? So again I will rotate this by 90, it will be somewhere here, and again this will touch here. Why? Because it's this angle, right? So what will be EF now? The new EF will be this. Let's say this is EF2 and this is delta 2, but again this right has to be constant. EF2 delta 2 has to be constant. So basically this condition needs to be satisfied. EF sine delta, sorry, EF2 sine delta 2 has to be constant. So basically what I am saying is EF1 sine delta 1 will be equals to EF2 sine delta 2. So basically how is it possible? It is possible only when this is in this length it touches. Basically the vector, right, always touch this triangle. The vector will always touch this triangle for any load current. For any load current, the vector will always touch this triangle. Then only your this right will be constant. This length will be constant. Okay. I hope you have understood this basic point. So what I am trying to say you is that here, as I am changing the power factor, the delta is changing. If delta is changing, so is the EF2. So if you observe one thing, right, here EF2 is higher and the load angle, what is the load angle here? So load angle is this, right? So load angle has reduced. EF2 is high, load angle has reduced. Here load angle was high, EF2 is lesser. So basically if I am increasing the excitation, right, visually also you can see if I am increasing the excitation, the delta is reducing. That means the sine delta will reduce, and it actually further satisfies our condition that EF sine delta has to be constant. So if one of the parameter increases, other one reduces. Okay. So now let me draw this graph. IA, VIA cos theta, right? So basically I am telling you that IA cos theta, IA is variable. IA is variable. If IA varies, cos theta will be vary also. Okay. But IA cos theta will be constant. IA cos theta will be constant. So how can I make IA cos theta to be constant? So what I can do is I can draw here my VT, I can draw my VT, okay, and this is my line. This line is important. Why? I will explain just in a second. Okay, so let's say this is my IA. And this is my theta. Okay, theta 1, IA 1. So what needs to be constant? IA cos theta needs to be constant. So if I draw a line along this, right, so let me first touch this here. If I draw the projection of IA along the VT, along the V, that will be constant. So this is basically what? This length is basically IA cos theta. IA cos theta, that must be constant. So basically I can go both ways, right? Either I can go in the right hand side, that means it is lagging. If I go on the left hand side, it will be leading. but it has to touch this graph, right? This line basically. Otherwise, IA cos theta will not be constant. So let's say this is IA2 and this is some other length, right? Some other length, very high length. Okay. So this is my IA2. This is my theta 2. But again, your IA2 cos theta must be constant. So basically, you can plot your current like this. Okay, your current will be in this whole along a straight line here, and your EF will always touch on the left hand side. So basically, I want to conclude. Now let's come to the conclusion. What do I really want to conclude? Right? I want to conclude one thing, that if I want to plot my EF and IA, if I want to plot my EF and IA, how will I plot? So my currents always will be along this straight line, that is this length will be constant basically, IA cos theta, right? This length will be IA cos theta. Okay, that will be constant. And one more thing, this length also will be constant. This length also will be constant. What is this length? This length is what? EF sin delta. So what happens is, for all of this E, right, it must touch here. It must touch here. So this is E1, this is E2, this is okay. Why it is E0? E0 I forgot to connect. E0 I forgot to connect. This will be E0, okay, and this will be E3, okay. So I hope you have understood this point. Okay, I forgot to plot the graphs as well. Okay. So this will be okay. It will be a bit messy. That's why I'm not plotting it. I'm not plotting the graph. So if you observe that initially E1 is, this is the E1, right? E1. And if you see, if I'm increasing the excitation, EF will always increase. That is already we have discussed about that, right? If I increase excitation, EF will always increase. If I increase excitation, EF will always increase. Okay. What is happening to the armature current? So if you notice carefully, if I increase excitation, the armature current is where? So for this pink line, armature current is here. Again, the armature current is for this blue line. Okay, so for this blue line, for this pink line, armature current is here. Okay, and for this blue line, armature current is here. Can you tell me which one has the higher length? Is IA1 greater than IA2 or IA2 greater than IA1? So of course, you see from the same point, I am tilting more angle, right? Tilting more and touching the same line. Okay, so obviously IA1 length will be higher. So basically, as I'm increasing my excitation, the current is reducing if power is constant. So what is, like, now is the time for conclusion. As I'm increasing my excitation, IA is reducing, but not always. If I notice here, as soon as I reach IA naught, okay, that is known as the normal excitation or nominal excitation. Here, what is the value? That is IA cos theta. That is IA only. Okay. Just after this, again what happens? Again the current is tilted, but this length will be constant, IA naught. So basically, your current, right, IA has two components. One is the vertical component and another one is the horizontal, right? So this component is fixed. It has to be fixed because power is constant. So it is basically, my IA current will be I vertical whole square plus, it's just a Pythagoras triangle, I horizontal whole square, right? This component is fixed, right? As there is angle, I am getting a bit of horizontal value as well, right? So IA is increasing. So if I move onto the left of IA naught or to the right of IA naught, IA will always increase. Okay, that is for sure. But remember, from where I am starting from leading power factor. Okay, where already the angle is very high, and I am reducing my angle, power factor angle. Okay, my theta angle. So initially, from under excitation, IA is reducing. Then what happens? We reach normal excitation. As soon as I reach normal excitation, then change happens. EF still increases. EF will always increase, right? Because IF is always increasing. But this time my IA also will increase. Okay, IA also will increase. What about theta? So if I say theta initially is reducing, right? This theta will determine the power factor. So initially theta is reducing because as I'm increasing the excitation, EF is increasing. If EF is increasing, sin delta is reducing. That is also known to me. Theta is also, if you see, theta is also reducing, right? If you see here, this was theta 1, then theta 2 is here. So it is reaching more closer to the V. V is fixed. So my current is reaching more closer to V. So theta is reducing. One more conclusion, theta is reducing. If theta is reducing, cos theta will increase, and that is expected, right? Because I'm reaching more towards unity power factor, because that is the aim, right? That is the aim basically. I'm reaching more towards unity power factor. Okay, because so as I'm increasing my excitation, initially it was leading. Now as I'm increasing the excitation, that means it is taking some amount of reactive power from the load, right? Sorry, it is delivering some amount of reactive power, right? Previous leading means what? Leading means it can only it can deliver, right? But I am increasing the excitation inside. Sorry, leading means it will absorb the reactive power from the load. But as I am increasing the excitation, so it does not need to absorb reactive power from the load. It has its own reactive power because excitation is getting increased, because the flux is getting increased. So please, if you are having confusion, in the previous lecture I explained this thing very well. Please go through it. Okay. So cos theta will increase here initially. After normal excitation, theta will, if you see, theta is increasing. If theta increases, cos theta will reduce. So power factor will get worsened. So this is the V curve. So if you see, that is what we have plotted, and this is the most famous curve, if you know, most famous curve, right? Okay, I hope you know this. This is known as the V curve. Okay, so in V curve what happens, and this is actually not symmetrical. Although you see it is symmetrical here, I will highly recommend you, it is not totally symmetrical. This is known as the V curves. V curve, V and inverted V curves. Okay, so so yeah, it is not symmetrical. That also I want to mention, that it is not symmetrical. Okay, so from under excitation I go to over excitation, right? So under excitation, over excitation, I'm increasing my excitation. Initially current will reduce, then it will increase, as I'm telling over here. Okay, initially current will reduce, then it will increase. Okay, so and for power factor it will just be opposite. So that's why it is called inverted V. It is like a V shape, right? That's why it is called inverted V and V curve. So this is for one I naught. If I change the load current, right? If the I naught is changed, let's say the load current is changed. Okay, I will copy this graph and I will take it to the next page. For different loads, this graph will be a basically a concentric V's and inverted V's. Okay, basically if I'm changing the loads, right? If I'm changing the loads, it will be a concentric V's. So basically if I increase the IA naught, if let's say this IA naught is IA naught and if I change it to IA1, right? If I change it to IA1 and IA1 is greater than IA naught, okay, then what will happen? Then basically this will increase, right? This will increase. Okay, so this will be, let's say for current, let me change the color. I1, this is IA0, right? So if I keep on increasing the current, let's say I go to IA2, so of course this graph also will shift upwards. Okay, graph also will shift upwards. Okay. One more thing is, of course, it will never touch, right? It can never touch because current will go very high. If you see, it can never go here. Okay, my IA current will not, can never go exactly 90. So this is tending towards, it is tending towards, right? These are basically, this will be parallel to each other. This will be asymptotes. Okay, these will be asymptotes basically. Asymptotes. Asymptotes meaning never intersect. Never intersect or intersect at infinity. Okay, and this side, the right hand side, is the zero power factor lagging. As I have increased my excitation very high, so it will deliver the lagging load. So the right hand side will be zero power factor lagging, and the left hand side will be zero power factor leading. Okay, right hand side will be zero power factor lagging and left hand side will be zero power factor leading. Okay, that is the case. Same will happen here as well. Like for no, okay, this will not change. Basically, power factor diagram will not change depending on the load current. That will not change. Okay, yeah. So what else we have to discuss? We have to discuss regarding the I guess if I am changing the current, right? If I am changing the current, then what will happen for unity power factor? Okay, now okay, this is happening for this load, right? If I am changing the current, it is moving. Okay, will anything else also change? Will something else also change? So right, it will not just go upwards, something else also might happen. Okay, so if I tell you that at unity power factor, what is the power? Power at unity power factor is V into Ia, and cos theta is 1. Power at unity power factor, right? So if I'm increasing the load current, then the power will increase, right? But of course, that power needs to be constant. So yeah, we cannot increase the load current. At unity power factor, we cannot increase the load current. Yeah, otherwise power will go high. No, that is not the condition. Yeah, this is the graph basically. These are the graphs. Okay, so this is the V curve and this is the inverted V curve. That's it. Okay. So I hope you have understood this basic point. Now let's solve few questions. Okay. I can show you the screenshot. This is the first question. Okay, and this is the second question. Okay, these two questions you try out by yourself and I will come with the solution. So let's solve this question, right? So a turbo alternator is connected to a three-phase bus that supplies constant voltage. Okay, it supplies constant voltage. Basically, I have a turbo alternator supplying constant voltage, and nowhere they have mentioned regarding the uh, armature resistance. So I will assume it to have synchronous reactance only. This is my EF. VT. Okay. Now what they're telling me that it is operating constant voltage frequency. If the steam supply of the alternator is suddenly cut off, okay, steam supply is suddenly cut off. That means the input power is cut off. Okay, what will happen to the alternator? That is what they're asking. So if the steam supply is suddenly cut off, what will happen? It will continue to rotate at the rated speed in the same direction. It will rotate in the same direction but at reduced speed. It will rotate at rated speed but in reverse direction. It will gradually come to stop. Okay, so most of the people will say that it will gradually come to stop. Okay, because he will say that input power is gone, right? If there is no input power, you are not rotating the shaft, automatically it will come to stop, right? You will see it. But no, this is not correct. Why it is not correct? because remember this is an infinite bus, and in the previous lecture itself we discussed the property of an infinite bus. What is the property of an infinite bus? Property of an infinite bus is, infinite bus is just like an ideal voltage source. It has the ability to deliver or absorb power. It has the ability to deliver or absorb power. Okay, so if suddenly the input to the prime mover is turned off, right, and still field excitation is there, and one condition has to be satisfied, that the phase sequence is same. Of course phase sequence will be same because already the this motor was synchronized, so phase sequence is same, right? Then sorry, generator was synchronized. What will happen? Then the generator will work as a motor. Basically this potential is fixed, so the infinite bus will now deliver the power, because motor will try to rotate only. Why it will try to rotate? Because DC supply, they have not told me that they have cut off the DC supply. Okay, they should have actually told here that excitation is still there, so DC supply is still intact. If DC supply is still intact and the motor is rotating, so what will happen? The MMF will try to rotate, and when it tries to rotate it will say give me power, I need power, right? Why it will try to rotate? Because due to alignment torque. All these have been explained previously, so I am going very fast here. Okay, due to alignment torque. So due to alignment torque, motor will say I want to rotate, but to rotate you need energy, you need power, right? How can you rotate? Either I can, with my hands I can rotate it, right? Either with my own hands I can rotate, or what I can do, I can connect this to a infinite bus that will deliver the electrical power that will help it to rotate. So yeah, then that's why the generator will work as a motor. So it will continue to rotate at rated speed in the same direction, provided it will rotate in the same direction provided phase sequence is same, right? If phase sequence is different, it will not rotate in the same direction. Phase sequence must be same. I hope you remember this, right? Phase sequence meaning that the peak of VA will be coming first, peak of VB will be coming later, then the peak of VC. Okay, this phase sequence has to be followed, otherwise it will just not, it will not rotate properly, okay, in the proper direction. It will not rotate in the proper direction. Okay, now let's solve the next question. So the V curve of an alternator is shown below. At the point where the armature current IA is equals to its rated value, okay, that's why it is 1 pu. Which of the following statements is true? The machine is more stable at point A, machine is more stable at point B, machine is equally stable both at point A and B. So how can you determine the stability angle? Okay, so this we will discuss later as well. We will discuss this later as well. For now, just one key point, I will discuss this, don't worry, I'll prove it to you later. Okay, for now just remember this, that the your whose delta will be lower, that machine will be more stable. Okay, so basically if delta 1 is less than delta 2, then I can say this is more stable for same power. How? So this we will learn later on. Why is this the case? I will explain later on. But for now, remember delta 1, if it has lower delta, it will be more stable. Okay. So here if I see that in this direction I am increasing the field excitation, and it is telling me it is a V curve, right? So V curve means basically power will be constant. So power is equals to E F Vt by XS sine delta, right? So power is constant, it is a V curve, right? Power will be constant. So I'm increasing excitation, so sine delta will reduce. and I want that. I want a lower value of delta. Why? Okay, sorry, I am not able to tell you right now. I will explain it in the next topic. Okay, so here, right, if I observe here, I'm increasing my delta. So this is point A where the E is very low, and this is the point where the E is excitation is very high. Right? If the excitation is very high, so here the delta required will be lower. The delta required will be lower. So at system B, at hence I will say, hence system will be more stable at point B. Okay, so point B is somewhere here. So option B, machine is more stable at point B. Okay, I'm sorry, I'm not telling you why. I will explain it later. Okay, now let's solve for the synchronous motor. For synchronous motor, something similar will happen, right? So here, this is the circuit diagram for synchronous motor. Okay, what is the now Vt is fixed. Again, it is connected to infinite bus. Vt is fixed. What will happen to E? That is what we want to do. So again, same conditions, right? And I think, okay, we have yet to derive the, what do you call, the magnitude of E and tan phi tan xi, all those things, right? We have not derived for the synchronous motor. So now we will discuss about that angle. Okay, so let us first assume that the synchronous motor is operating at lagging power factor. If it is operating at lagging power factor, what will be the phasor diagram? What will be the phasor diagram? So from here, what will be EF? So EF will be equals to, here it we missed, yeah, it will be V minus IA RA plus J XS. Okay, so this will be my V, this will be my V. So here what I can say, with respect to V, right, IA, it is lagging power factor, lagging power factor. If it is lagging power, this is Vt. So IA will be somewhere here. And this is theta. Okay, what about what will be E then? So E, right, remember this is minus sign, so minus I into RA. So minus will be just the opposite, right? 180-degree phase shift, so it will be here but just opposite. So 90 and 90, so it will be here. This will be the IRA. So I can reduce this length. Okay. Excuse me if it is not exactly anti-parallel. So this will be my IRA. What about the other one? This, right, minus J into IXS. So it is minus 90. It is not plus 90. It is minus 90. So minus 90 will be this, right? Minus 90. Minus 90 will be in the anti-clockwise direction, not in the, sorry, in the clockwise direction. Am I right? Yeah. Minus 90 will be in the clockwise direction. Okay. So this is minus 90. And this is IA into XS. Okay, so like it will just be the opposite. The lagging case will be just same as the leading case of the what? It is just dual, right? Leading case of synchronous motor. Actually, the better thing would have been if I would have done both of them together. That's the better thing. That's my mistake. I did not do it. Okay, next time when I will teach, I will do them together. Synchronous generator, right? The leading, just go back to your pages, check the leading case of synchronous generator. You will see same thing is happening. Okay, so now I can directly say this will be my EF. This will be my EF. Okay, so this is my delta. This is my delta. Okay, so yeah, I hope this is clear. Now we want to understand what will be the value of EF, right? Magnitude of EF. How can I derive the magnitude of EF? So the magnitude we can understand with two components. Okay, one will be the perpendicular component and the parallel component. Okay, so basically EF, right? EF will have two components, one along the projection of VT. So this, what will be EF cos delta? Again, right, same thing I can derive. If it is unity power factor, EF cos delta would have been directly, I think it would have been directly, yeah, IA into RA minus IA into RA. Okay, so EF cos delta will be here. This will be equals to, let me first do it for the unity. Actually, the better thing would have been to do it for the unity power factor. Okay, let me just give me a break. I will do it for the unity power factor. Okay, so this, let's take this as the second case because unity power factor will be the easier one, correct? So unity power factor will be the same as the synchronous generator. Okay, let me do it for the, so unity power factor, right? One first case, unity power factor, very simple, right? So your, yeah, this is your V minus IA array. So IA will be in phase with, IA will be in phase with VT. So minus IA array. IA array will just be opposite of IA. Okay, what about I axis? So j into minus j into I axis, right? Minus j into I axis will be just basically 90 degree, minus 90 of this, minus 90 will be here. Okay, this will be minus j into I axis. So I axis will be here and this will be my EF. Okay, so now I will derive, right, one thing. I want to derive the length, and what is the psi? Remember what is psi? Psi angle was the angle between the EF and IA. Okay, all these angles I have you remember, right? For generator we derived, right? It is the internal power factor. Okay, so unity power factor, if I say, then I can say I can break this down into two components. One will be along this component, one will be along this component. So this length will be same as this length, right? Okay, that is gone. Somehow that is gone. Okay, IRA is gone. Sorry. Yeah, it should be here, right? It should be negative. Okay, my bad. Actually, yeah. Because here, right, see, minus IRA is there. So minus IRA, then I will add minus JIXA. So JIXA will be coming here actually. Sorry, my bad. Yeah. So I'm just doing phasor. So I am expecting you know enough phasor, right? I'm expecting you know enough phasor. I'm not explaining phasor. Okay, मेरा काम हो गया. Phasor और मैंने explain नहीं करूँगा. Okay, so Now here, right, two components, one will be along this component, other one will be along the this component. So so EF cos delta, if I see, is equals to your VT minus IRA, right? Because this overall length is VT, but I am subtracting IRA. So EF cos delta is this value, and my EF sin delta is only this component, right? IA into XS, because I don't have any component, horizontal component, only this component is there, IA into XS. So from here I can directly say what will be my EF. So here also we could have said it directly. It will be basically under root of V minus IA array whole square plus IXS whole square. Okay, so this is what my EF will be equals to. Okay, in case of a unity power factor, and this is same as delta, so I'm not deriving it. So so what will be tan delta? Tan delta will be what? So these things you can derive, right? Draw the phasor diagram and derive it. If they ask you, you don't need to, like, I'm writing this down. It's not like you have to remember this. No, draw the phasor diagram, understand it, develop the intuition. Okay, so what will be tan delta? Just take the ratio of these two, right? It will be IAXS divided by VT minus IA RA. Okay, now what about here? So this time, right, remember this is theta. Okay, if this is theta, this also should be theta, I guess. So this is theta, so if I extend this, right, this will be theta, right? This is theta, this will be theta, correct? This is theta, this is theta. Okay, basic geometry class 8 9. Okay, I will not explain, okay, this is theta. So now this is a right angle triangle, right? So this is 90, so this will be 90 minus theta, correct? This will be 90 minus theta, so this will be 90 minus theta. Now if this is 90 minus theta and this is whole 90, so this will be theta. Okay, this will be theta, again class 8 9. Okay, class 8 9, so this will be theta. Now this, right, IAXS component has two components, one is along this, another one is in the bottom, and this also has two components, one is along this, other one is bottom, right? I will write those components. So I want to write first of all the EF cos delta component. So IRA cos theta, IRA cos theta, correct? So it will be VT minus IRA cos theta. Okay, and what I can write? I can write, okay, yes, and okay, I don't want to write in terms of delta, I want to write in terms of psi. Yeah, that is also correct. I want to write in terms of psi. Okay, one very big mistake I had made is your angle delta, right, in case of motor will always be negative. Why it will be negative? Okay, very big mistake I had made. It cannot be positive. How it cannot be here also, it cannot be positive, right? Okay, somewhat of a big mistake I have made. Okay, actually, yeah, so yeah, my bad. So I had made a big mistake here. So this like, what is this? So we'll break this down. EF is equals to V minus IRA minus J IAXS, and remember it is unity power factor, so IA does not have any phase angle, IA is IA angle 0. So it is minus IA array, which is here. It is minus j into IXA. Minus j means rotate in the clockwise direction with respect to IA. I rotated in the clockwise direction with respect to minus IA. That was my mistake. I'm sorry. So I had to rotate with respect to IA in the clockwise direction, right? So if I do minus 90 here, it will be in this direction. I'm really sorry. And it is actually conceptually correct. We were conceptually wrong there. Okay. Also, we got to a result, but that was conceptually wrong. I will explain why it is conceptually wrong. Because in case of motor, the power angle will be negative. Why it will be negative? Because the infinite grid will deliver the power. Hence, delta will be here. Delta will be here. Okay, and psi will be here. Okay, so now the important fact is why it will be negative, because the formula will not change. Formula will still be this: P equals to EF Vt by xs sin delta. But this time the P will be negative. Why it will be negative? Can you tell me? Because it is absorbing power. It is not delivering, it is absorbing power, right? Motor cannot deliver power, it is absorbing. That's why here I have minus delta. That's why here I have minus delta. Okay, although I should not write it like minus delta, I should just write it delta only, but because otherwise you will get confused. Right? Minus delta signifies that it will not lead, it will lag. Okay, it will lag here. Okay, that is the important part. P will be negative. That's why sin delta has to be negative. That means delta has to be negative. That means it has to be in the clockwise direction. Okay, same here. No matter what, EF has to be in the clockwise direction. It cannot be in the anti-clockwise direction. Why? Because motor can absorb power. It cannot deliver power. Motor can absorb power. It cannot deliver power. Okay, so delta will be negative. So what went wrong here? What went wrong here? So the thing that went wrong here is this, right? This should have been, first of all, this is fine, IRA, and this, with respect to this, I had to rotate in the clockwise direction, this, right? So it will be somewhere here. Okay, okay, let me do one thing. Let me bring it more near. Okay, otherwise the diagram you will not be able to understand. Bring it more near. This IA. Okay, so this will be minus 90 here. Yeah, now it is fine. So this will be EF. Okay, this will be delta, it will be negative, and this will be IXS. This will be my EF. Okay, now I hope everything is clear. Okay, now if I try to plot with respect to, remember what is psi? Psi is this angle, right? Because they might ask what is psi. Psi is this angle, the angle between internal power factor, the angle between the EF voltage and the IA current. So psi is what? In this case, psi, this is wrong actually, this is wrong. Psi is actually theta minus delta. Psi is theta minus delta. Okay, now how do I find out psi? That is the question here. How do I find out psi? So what we can do is we can have all the components along the direction of this psi, correct? So if I notice one thing, right, okay, this is exactly not anti-parallel. It seems it is not exactly anti-parallel here. Actually anti-parallel is here. Okay, so uh, how can I determine the psi angle? How can I determine the so what I can do is I can project this Vt along this Ia, right? What will be the projection of Vt along Ia? It will be Vt cos theta, correct? Vt cos theta. So the projection of Vt along Ia will be Vt cos theta. Let me do one thing. Let me copy this. Okay, otherwise you will get confused. Let me copy this thing. So along Ia will be this, right? So this is what this I will mark in here, and this will be my Vt cos theta. Okay, what other components I have along this, right? I had this Ia array, right? So Ia array is just in the opposite direction. Ia array is just in the opposite direction. So I have to subtract Ia array from this, right? Ia array is just in the opposite direction. That will give me what? That will give me the projection of EF along this Ia, correct? That will give me the projection of EF along Ia. So if I project EF here, right? If I project EF here, so this is the projection of EF along Ia, and this projection Vt cos psi Vt cos theta is this much. What is this much? This much is this. It is just parallel, right? It is just parallel. So this length is this length is I array. Okay, so basically the conclusion is my EF cos psi will be equals to Vt Vt or whatever V you want, you can say Vt cos theta minus I array. Okay, now what is the perpendicular component? What is the perpendicular component? So the perpendicular component is this one, right? Also Vt is there, don't forget Vt. Okay, so basically this is the component along Ia. I have another component that is perpendicular to Ia, right? That will be here. It will be perpendicular to Ia. Is it perpendicular totally? I think this one is, no, this is not 90, this is 90, I guess. This is 90. So this component is perpendicular to Ia. So this is EF sin xi. Okay, EF sin xi. So this is EF sin xi. Okay, this is EF sin xi. So what I can say is, what is EF sin xi equals to? So Vt has its components along Ia, that is Vt cos theta. Another component will be there that is perpendicular to Ia, that will be Vt sin theta. This will be Vt sin theta. And again the same thing, right? Again if you see this length, right, Ixa is getting subtracted here, so that I am getting EF sin psi. So EF sin xi equals to Vt sin theta minus IA xs. Okay. So now can you simply find out what is EF? So EF will be what? If I take the whole square and take the under root, I will be able to find out EF. So EF will be Vt sin theta, sorry, Vt cos theta, or you can write any one you like first, IRA whole square. Just I'm squaring and then adding the both two and then taking the under root, right? So sin square theta plus sin square xi plus cos square xi will be 1. So on the left hand side I will have EF square, which will under root, so it will be EF only. On the right hand side it will be plus Vt sin theta minus IA xs whole square. Okay, so and what about the angle tan xi? Tan xi will be what? Just the ratio of these two, right? So it will be Vt sin theta minus IXS divided by Vt cos theta minus IARA. Okay, exactly it will not, because I think there, right, minus IARA was not there. So actually I was kind of wrong that exactly it will be just dual, kind of wrong, right? Because the motor is receiving the power, right? So that's why the drop is negative. There the generator was delivering the power, that's why the drop was positive. So EF will be somewhat reduced because IA current is flowing here, right, through the armature resistance. So EF value will be somewhat reduced. But here EF was there in case of generator and this was the receiving end. So here the drop has to be considered in EF for generator. Okay, this is how you can remember. Okay, so for a leading load I will derive. So let's now do it for the leading load. Lead power factor, leading power factor. Okay, so for leading power factor, what, like, remember this, E will always lag Vt. Okay, that is always true. So we will see, like, again the same formula, right? The formula is Vt will be somewhere here. Okay, Vt will be somewhere here and current is leading. If current is leading, then current will lead somewhere here. Current will lead somewhere here, right? It will lead. So this will be my IA and this will be my Vt and this will be my theta. And remember, E will always lag Vt, right? E will always lag Vt because active power will be sent from the terminal infinite bus to the motor. That's why. And this will be your delta. So this time what is your xi? In case of leading load, the xi is addition of theta and delta. Okay, so xi, the internal power factor angle, will be theta plus delta, right? Just the opposite in case of a generator. Just the opposite in case of a generator. Now let me derive the very basic equation. So the very basic equation is that my EF will be equals to Vt minus J minus IARA minus J J IA XA. Okay, so what is IARA? IARA is somewhere here. IARA minus IA, so IA is in this direction, minus IARA will be in this direction, right? So just anti-parallel to this, I have to rotate a whole 180, and of course the drop will be much smaller. Okay, drop will be much smaller. Now what about JIA access? So minus JIA access should be, plus J will be here, minus J will be somewhere here. Okay, so kind of this is wrong. So what I will do, I will increase this right here, and let me go put this here only. Okay, and minus JIA access will be 90° in the clockwise direction of this, or in the anti-clockwise, this, right? This will be the minus J. So basically plus J will be what? Plus J will be this, plus J will be here, minus J will be here actually. Okay, sorry. Yep, what will be plus J? Plus J will be in the, yeah, clockwise direction. So this is my direction. Sorry, this is my direction, right? Yeah, plus J will be here. Okay, minus J will be in the top side. Sorry, minus J will be in the top side. Sorry. Yeah, minus J will be in the top side actually. Here. Like basically my IA direction is in this direction, right? If I am multiplying plus J, basically it tells me that rotate this vector in the anti-clockwise direction by 90°. That means this will be plus J. But if I am multiplying minus J, that means rotate this vector in the anti-clockwise direction. So in the clockwise direction. So I rotate it in the clockwise direction. Okay. So that's why this direction is here. Okay. Please understand the phases very well. So this will be IRA. This will be minus J IA XS. Right. Now the combination of these two will be basically my E. Right. So what will be the values basically? So now if I want to write my E cos in two components, right? If I want to write in two components, one will be along this IA component, one will be perpendicular to this IA component. So perpendicular to this IA component is this one, and VT also is somewhere here, right? So it will be, so again if I break down the components, this let me delete, or let me keep it only for your better understanding. So if I keep it over here, so this VT will have two components, one will be along IA and one will be perpendicular, projections basically perpendicular to, okay, IA. Okay, so this will be what? This will be VT cos theta, this will be VT sin theta. Okay, sorry, yeah, perpendicular to, sorry, perpendicular to IA will not be exactly in parallel, right? It will be somewhat here, correct? Yes, somewhat perpendicular will be here, right? Yeah, exactly, this perpendicular is same as the, same as this, right? Same parallel to this. Okay, and this E also will have two components, right? One will be along IA. What will be the value of that component? Value of that component will be E F cos, or you can directly write E cos xi. Okay, and the other one right? That will be perpendicular, projection will be perpendicular E sine xi, okay? So it will be E sine xi. So now, yeah, so what will be my E cos phi equals to E cos I equals to E cos I will be equals to this, right? This Vt cos theta minus IRA, because IRA is in the opposite direction. So IRA will be in this direction, right? Both are parallel. So Vt cos theta minus IRA will give me E cos xi. Okay. Don't be in this delusion that this length is higher than this, but it is just visual. Okay, actually Vt E cos xi will be much lower depending on the angle xi, right? If xi is higher, obviously the component will be lower, correct? So it will be Vt cos theta minus Ia into I. Okay, so this will be the value of the E cos xi. What about E sin xi? E sin xi, if you observe here, it is addition of two, because both of them are in the same direction. Vt sin theta and this both are in the same direction. Here Vt cos theta and IRA were in the opposite direction. That's why subtraction. Here both of them are in the same direction. That's why addition. So it will be, I'm just considering the length. I'm not considering the angle. Angle is already taken care of, right? By drawing the vector. So it will be Vt sin theta plus Ia xs. So from here I can get down the relations, that what is my E will be equals to again the same thing, right? It will be Vt cos theta. Okay, I need to, okay, I will write in the next page. Cos theta, this will remain change, right? Remain same. The other part will change. This time this will be Vt sin theta plus IRA, right? It becomes plus XS, right? Previously it was minus XS in case of a lagging load. Now it is plus XS for a leading load. Okay. Again, intuitively, how you can understand? Intuitively, you can understand that, of course, if it is a leading load, if my load is leading, that means synchronous motor is a leading load, that means what? Extra flux is getting delivered. If extra flux is getting delivered, that means E will be higher. That's why here the E is higher in case of a if the synchronous motor is operating at leading power factor. Okay, that's why that is the physical significance basically. That is the physical significance. I hope you have understood this point. Okay, so but of course it can be lower as well depending on the IARA value. If it is lower than VT, I'm talking about. Okay, depending on all those values. So this is my E. What about my tan xi? What will be tan xi? Tan xi, right? Tan xi will be, okay, tan xi will be this ratio of these two, right? This one and this one. So it will be Vt sin theta plus IXS divided by Vt cos theta minus IRA. Okay, so this is my tan xi and this is my theta. So like what formula you have to remember? you just remember for the leading case. Okay, for lagging case, what you can do, you can just replace for leading this was the okay, it was here plus here. For leading case, you remember, for lagging you just replace excess with minus excess. Okay, here also you replace excess with minus excess. Here if you replace excess with minus excess, this will become plus, this will become plus. Okay, how can you understand intuitively? Intuitively you can understand that as it is operating at leading power factor, that means more flux is getting generated. That's why the excitation will be higher than the lagging case compared to, this will be lead compared to lag E, right? This will be higher. Okay, how to remember the formula, that also I have explained. Very simple, just replace your excess with minus excess, everything will be sorted. Okay, and your psi, remember your psi this time is theta plus delta. Previously it was, if you see here, it was theta minus delta. Okay, now what are the key points? The key points is that for a generator, uh, uh, what was the main thing for a generator, right? For a generator, the E will always lead V. Okay, that means power flows from E to V. Okay, for a motor, E E will always lag V. That means power flows from V to E. Very important thing. This is very, very important. Okay, don't forget this. And of course, I have already have solved, derived the formulas. You can remember the formulas. Okay, that is up to you. So same thing, whatever I have discussed, same thing is written over here. What will be the armature reaction? So armature reaction in case of a lagging power factor will be magnetizing. Why? Because motor draws the reactive power from the supply. Okay, motor is drawing the reactive power, because like this is my supply, right? And if I say that the load is operating in lagging power factor, that means what? Q is coming in. If Q is coming in, that means it is operating, it is magnetizing. Armature reaction will be magnetizing. Okay, now if it is leading power factor, that means what? This is my bus. Okay, and here I say that okay, this is excess, and here I say that it is leading meaning it is delivering reactive power. If it is delivering, then obviously the internal magnetic flux, main field flux, is getting reduced. So armature reaction is demagnetizing. Armature reaction is demagnetizing. Basically, my machine was overexcited. Let's say you have 1000 rupees, right? And you only require 500 rupees. So you are overexcited. So you will give the 500 rupees to your brother or sister. I know you will not do that, okay? But good guys, good elder brothers and sisters will do it, right? So same thing, motor has too much of excitation. That means EF is high. So it will deliver some of its excitation to the load. Okay, that's why it is operating in leading power factor, right? And here it is operating in lagging because it has less. So you have only 250 rupees. So you will ask money from your elder brothers or sisters, right? So reactive power it is getting in. So it is operating in lagging power factor. Okay. So that is the case over here. And unity power factor, it is operating, the armature reaction will be cross magnetizing. Basically it will represent normal excitation. Here it will represent over excitation for leading because it has more flux. Here it will represent under excitation. So remember, in generator motor everything is different, right? Just try to understand the analogy. Understanding the analogy is very, very important, otherwise you will mess it up. Okay, if you just remember, right, try to remember it, write down in your formula notes and remember, okay, leading means overexcite, lagging means underexcite. You will not understand it, right? You'll forget it, you'll mess it up. So please understand it conceptually what is happening. Here motor does not have enough magnetic flux, so it is requiring reactive power, so it is under excited. Okay, here it is overexcited, it has enough magnetic flux, so it is delivering reactive power, so it is overexcited. Okay, please understand this. One day gate will frame a MSQ, right? You will get confused. Okay, and these were the formulas as we discussed here. Whatever we discussed, the same thing is written over here. Okay, mechanical power developed we will discuss in the next lecture, don't worry about it. Let's solve few questions. Okay, so this is the first question, and this is the second question, and this is the third question. Okay, so these questions, pause the video and try it out by yourself, and I will now solve these questions one by one. Okay, so let's solve this question. Let's solve this question. Okay, so here a synchronous motor under load draws current at leading power factor. So synchronous motor is operating under load and it draws current at leading power factor. So basically, if this is my Vt, so current will be leading, current will be somewhere here, I, this theta. Okay, and this is phi, it is operating at leading power factor with phi. If the internal power factor angle, again your E will always lag no matter what the Vt. So this is delta. Internal power factor angle is defined as the phase difference between the excitation EMF and the stator current in time domain phasor diagram. It is denoted by psi. Then the angle by which the air gap excitation MMF lags the armature MMF. So what will be the direction of armature MMF along the direction of the armature current? So this will be the direction of the armature MMF, right? Okay, this will be the direction of the armature MMF. And what will be the direction? What will be the direction of this excitation EMF, right? Induced excitation EMF. So direction of induced excitation EMF will be 90-degree leading, right? Because induced EMF will lag by 90-degree. That is what we know, right? Induced EMF lags by 90-degree. So okay, this feels like it is also almost 90. So I will not let it feel like that, right? So let me rotate it a bit, right? Let me make it more steeper. Let me delete it actually. Let me make it more steeper. Okay, this is my delta. So it will lag. So somewhere around here, my main field flux will be there, right? Main field flux. But what they are asking actually? Are they asking main field flux direction? They are asking me the angle by which the air gap excitation MMF. Excitation MMF basically means the main field MMF they are talking about, right? Excitation MMF basically they are talking about the main field MMF. Okay. So if you are doing this right, you are wrong. Why you are wrong? So I will explain a very important thing. So when we were doing it for generators, okay, we had a generator here, right, and we had this infinite bus. So I was saying this is my EF and IA was going out. Okay, so IA was positive according to this EF. If IA is going out, it is positive, right? Then we drew a phasor diagram. Let's say if it's a lagging load. If it's a lagging load, my EF will be here, my FF will be here. Okay, and let's say it's a lagging load, purely lagging with respect to EF, it is purely lagging. If it is purely lagging with respect to EF, IA, that is, so it will be somewhere here. So the armature MMF will be somewhere here, FA. Okay, now same thing, how can I write for a motor? For a motor, bit of different things will be there for a motor. Okay, for a motor, if you see, now Vt is coming out of Ia, right? This is Vt, Ia is coming out and it is going into the motor. Coming into the motor. So the motor is absorbing power. Motor is absorbing. So with respect to motor, it is minus Ia actually. How? If I say Vt is delivering, that means Vt into Ia is positive power, then how can I say that motor is absorbing? I can say minus EF into Ia. So EF is positive number, so Ia has to be negative, right? If I say this is delivering, positive is deliver, then negative has to be absorbed, so it has to be minus Ia. Okay, So whenever you are drawing the MMF, you have to draw with respect to minus IA, not plus IA, because IA is incoming to the motor. Okay, very important thing. No one will tell you, and everywhere else, right? In the solution of this question, you search it up, you will find everywhere else it is written wrong. Okay, everywhere else it is written wrong. So with respect to motor, what will be the, for a lagging load? This I am discussing for a lagging load, purely lagging, right? Like if the internal power factor is basically 90 degree, okay, lagging load. For a motor, if my EF is here, right, and if it's a lagging load, where will my IF lie? Remember basic thing, very basic thing is there, that if it's a lagging load, right, if it's a lagging load, it lags with respect to what? It lags with respect to Vt. And if Vt is Vt angle 0, it will be IA angle minus 90. Okay, it will be IA angle minus 90. So minus 90, if Vt is along, let's assume that reference is this, right, 0 degree, for a second, just assume minus 90 will be somewhere around, okay, here only. But you know, you will not draw here, you will draw minus IA here. Why I will draw? If you notice one thing, if the load is lagging, that means what? That means I am sending reactive power, right? Reactive power, the motor is receiving reactive power. That means obviously armature reaction should be magnetizing, because I am giving reactive power, so obviously it should support the field flux, it has to be magnetizing. So basically whatever the direction of the armature reaction MMF should be along the direction of FF, it should support the field flux, right, because I am delivering the reactive power. So I will just discuss, because this is a confusing topic for motors. Whenever discussing about reactive power, so discussing about the not reactive power, discussing about the magnetizing, demagnetizing and magnetizing effect, you just think in terms of reactive power. Okay, basically you make your IA to be negative, minus IA. So what if IA is here, right? IA minus 90 should be here, actually your minus IA will be here. So you write in terms of, you write the direction of the MMF according to minus IA, not with respect to IA. Okay, just to clear out the confusion. So here the direction of the MMF will be totally 180 degree apart, not here, it will be 180 degree apart. So I will now will draw. So if my Vt is here, okay, this is my Vt, and my E will always be lagging, this is my delta, I is here, it is a leading current, so this is my phi. Okay, so my FA will be opposite direction, so FA will be in this direction, this will be FA. What about FF? So FF, right, again I have to make it a bit steeper, otherwise again you will get confused. It will be here. Okay, so this will be my FF. Okay, so now can you tell me what is the angle between FA and FF? Because what they're asking me how much, by which angle air gap excitation MMF lags the armature MMF. Why lags? Because if I start from armature MMF, I have to move in the clockwise direction. So it is exactly correct. It will lag. It will lag, right? So what will be this angle? How do I find out this angle, right? Okay, sorry, this is exactly not here. This should be somewhere. This should be actually somewhere here. Somewhere here. Okay, so now this angle, remember, okay, I will draw the angles. This angle is 90. This angle is 90. And this angle is xi. Okay, so this angle is xi and this angle is 90. I have to find out this angle. How will I find out this angle? So what do I know? That this angle is 180, right? This whole angle is 180. Okay, this whole, it is a straight line. It is whole angle is 180. This much angle is xi, that is internal power factor angle. So what will be this angle? This angle will be 180 minus xi. Now what will be this angle? So this angle is 180 minus xi, this angle is 90. So this whole thing should be 360, correct? So this will be basically 360 minus addition of these two. So it will be 90 plus xi. Okay, so basically this angle, right? This total angle should be 360, right? So this plus this is 270 minus xi. So I have to subtract this with 360. I will get back my angle. So 360 minus 90 is plus 90, and minus of minus xi will be plus xi. So your angle between the armature MMF and field flux MMF will be 90 plus xi. You go solution, you search the solution. This is actually a GATE 1995 problem. Okay, everywhere else the solution is given wrong. Everyone will do the solution wrong. Okay, because they don't understand the concept. So answer will be 90 plus 5. Everyone will mark this pi by 2 minus xi, right? Everyone will mark this, and all of them will be wrong. Okay, all of them will be wrong. So just be yeah, careful regarding this. So answer to this question will be 90 minus xi. This is actually a very good question. Okay, this is a very good question. Okay, now let's solve the next question. Okay, 90 plus xi, 90 also they have written in pi by 2. So I hope you understand. They have just converted into radians. Okay, so here they are asking, a three-phase synchronous motor is operating in the clockwise direction. What will happen if the direction of the field current is reversed? Okay, so they are asking, if I am changing, if I reverse the direction of the field current, what will happen? So basically, in case of a cylindrical rotor, these are my north south poles, right? And it is a motor, right? So basically north south poles is fixed and there was alignment torque, and my these are my three phase balance supply, which let's assume that the three phase balance supply was rotating in the clockwise direction with speed ns. So my synchronous motor also will rotate in the clockwise direction with speed ns, because there has to be alignment torque between the rotor field and the stator field. Okay, now they're telling me that they have changed the direction of the mean field flux, that is the field excitation. So the north pole will be here and south pole will be here. Will it make a difference? Will it make a difference? So actually they will not make a difference. Why? Because let's assume, obviously the stator magnetic field will also have its own north and south pole. So we know that here there was a connection between the north and south pole. S, the green one, is the stator poles, right? And here I had a connection between the north and south pole, right? This alignment torque I have already discussed in the first lecture. Okay, first lecture of synchronous motor. So they were aligned, and as the stator magnetic field or stator poles were rotating, so is the rotor, right? But here suddenly what happens? My south pole is still here and north pole is still here. What will happen? But remember, they are not discussing about the stator current. So stator current, the phase sequence of supply is same. phase sequence of supply chain. So if phase sequence of supply chain, still the stator will rotate in the clockwise direction with n speed. What will happen to the rotor? What will happen to the rotor? So to the rotor, basically what I can say, that south poles will repel each other and north poles will also repel just for a fraction of a second. So after one half cycle, what will happen again? Of course, the stator magnetic field is rotating. If the stator magnetic field is rotating, my windings are here, but the stator south pole will come here, north pole will come here. Still, let's say rotor has still the south pole here, north pole here. Again, they will form a bond, that is alignment torque, and again they will rotate in the same direction. So they will actually continue to rotate in the same direction. Option A will be correct. Many people will think that motor will reverse its direction of rotation, right? No, nothing like that will happen. They will continue to rotate in the same direction. Okay, so this is a trick question. Now let's solve this question. This question is again very important. With this, again, your like understanding of the armature flux and all those things will be more and more clear. A round rotor, basically that means cylindrical wound rotor, operating under load, draws a current at leading power factor. Okay, so it is drawing a current under leading power factor. So again, if it is drawing a current under leading power factor, so I will draw the phasor diagram very well here. Okay, so let's say this is my VT. Okay, and what will be my IA? IA will lead the VT, so IA will be somewhere around here. Okay, so this is theta, this is IA. Okay, this is VT, and what can I say is EF will lie somewhere around here, right? Somewhere around here EF will lie. Okay, not exactly 90, I can say somewhere around here. Yeah. EF will always lag VT in case of a synchronous motor. Okay, this will be EF, basically this will be angle delta. Okay, now they are discussing about air gap MMF, they're discussing about armature MMF. So let me draw the air gap and armature MMF, right? So the armature MMF will be just in opposite direction to the armature current. Okay, just 180 degrees. So armature MMF will be in this direction. Okay, so this will be F armature, right? And the okay, this, right, again it seems like it is 90. Why does it seem it is 90? Let me make it more and more shorter. This is EF. Okay, so yeah, so now what I can say is yeah, FAR is here. So what will be the direction of the main field MMF? So main field MMF will be somewhere 90 degree lagging, so it will be somewhere around here. Okay, somewhere here. Okay, so this will be my main field MMF, and the internal power factor angle xi is this one. Okay, so now let us solve the question, whatever they are asking. Now we are very comfortable. And what will be the resultant? What will be the result? Are they asking the resultant air gap MMF? Yeah, resultant MMF also they are asking. So what will be the resultant MMF basically? So this, right, FAR will have two components. Okay, so FAR will have two components. One will be cross magnetizing, one will be demagnetizing. So this, right, if I want to add, like, overall flux will be what? Resultant flux will be FF plus FAR. So if I add this one, right, if if I add these things, so I will get my FR. This will be my FR. Yeah, one mistake. Actually, FAR will not be this large, right? Field armature MMF will be very small actually, not this large. That's my fault. Obviously, it cannot, like, length of armature MMF cannot be higher than field MMF, correct? So actually, FR will not lie here. So this will be the addition. So can write this here. So my FR will lie somewhere around here. Does it intuitively make sense? FR lying somewhere around here, it actually does, right? Why? Because roughly, right, what we say is whenever we are discussing about FR, VT is roughly equals to ER only, right? We neglect the drop, we neglect the other drops, we roughly say it is ER, okay? We neglected the drop across the synchronous impedance. So VT is roughly equals to ER, and we see that our FR is 90° lagging the ER. So flux is here, right? Flux should be here. So which is absolutely correct. Okay. So whatever we have drawn is absolutely correct. Okay. So this is the about the ER. So now what about the angles? What will be the angles now? So yeah, let us discuss slowly. So the angle by which the air gap excitation MMF and the armature MMF is. So air gap excitation MMF. Air gap excitation means it is talking about the FF and the armature MMF. Angle between FF and FA, right? FF is here, correct? And FA is here. What is the angle? We had just derived it. The angle was 90 plus 90 plus this xi, right? That was the angle actually. We had just derived it, correct? So here the angle will be 90 plus xi. Okay. So this one we just derived it. Which in the previous one only. What was the load here? The load was leading. Here also the load is leading only. Okay. So I can derive it again. Okay. So this angle is xi. Okay. And this angle is 90. Right. This angle is 90. This angle is xi. Or I can say, okay, this angle is 90. This angle is 180. This whole is 180. Right. So how much will be this angle? This angle will be 180 minus xi. What will be this angle then? Now this angle is, I need to find out this angle, right? So this angle is xi, this angle is 180 minus xi. So this angle will be basically 360 minus this value. Okay. 360, okay, sorry. Yeah, 360 addition of these two. Okay, anything I'm doing wrong? Sorry, this angle, right? Okay. What will be this angle? Okay, this angle is this much, this angle is this much, and I need to find out this angle, right? Okay, this angle is still left. Okay, this is not enough actually. So how much is this angle? This angle is 90, right? This angle is 90, correct? This angle is 90. So this angle will be what? This angle will be 90 minus xi. Okay, so this angle is 90 minus xi, and we know, okay, we have to find out this angle, right? How will I find out this? Okay, how will I find out this angle? So this whole thing is 180, right? This whole thing is 180. This whole angle is 180, and this much angle is 90 minus xi. So what will be this much angle? So 90 minus xi plus theta x, right, will be equals to 180, right? This whole angle is 180. It is just opposite, right? This whole angle is 180, and this much angle is 90 minus xi. So this plus theta x, this is theta x, let's say, is 180. So from here I can directly say the answer of 1, theta x will be equals to 90 plus xi. So for the first one, 90 plus xi, we had already derived it. Okay, it will be 90 plus xi only. For the first one, it will be 90 plus xi only. Okay. What about the next one? The angle by which the resultant MMF and the armature MMF leads or lags. So resultant MMF and the armature MMF. Okay, sorry. We okay. Now we are discussing about the resultant MMF. Now we are discussing about the resultant MMF, right? Okay, previously we discussed about the field MMF. Now we are discussing about the resultant MMF. So resultant MMF and the armature MMF. How will I find this out? So I have to find out this angle. So this much angle I know 90. This much is 90, right? So what is this much angle? So for the second one, we'll copy. Otherwise, it will become a mess. Okay. Okay. So I know this much angle is how much? This much angle is 90. So this is 90, right? FR and VT will have angle 90, right? FR and VT will have angle 90, and this much is theta. So it is 90 minus theta. This much angle will be 90 minus theta. Okay, this much angle is 90 minus theta. Now I know this whole angle is 180. I know this whole angle is 180, and I know this much angle is 90 minus theta. So what will be this? Again the same thing, right? So again, theta x plus 90 minus theta will be equals to 180. So again theta x will be equals to 90 plus theta, and my FR will lag the armature reaction. If armature MMF, right? So it lags by 90 plus theta. It lags by 90 plus theta. So here it will be lags by 90 plus theta. 90 plus theta is not even present in the option. Okay. Resultant MMF it will lag only. Resultant MMF will lag the armature MMF by 90 plus theta. Correct? It will not lead. Okay. Can I say will it lead? No, lead I cannot say. Lead will be from here, right? So actually this is kind of wrong. It should be lag 90 plus theta. So this, right here, option C, it should lag. It should not lead. Option should be lag here. Okay, my bad. This option should be lags. Okay, here also it is wrong, right? The air gap excitation MMF lags the armature MMF. It should lag. Okay. All these options should be changed actually. All this should be lag. I noticed now only. It should not be lead. It should be lag. Okay, my bad. Okay, it should be lag here. This also should be lag. Okay, so option A will be correct. Sorry, not option A, sorry. Option C will be correct. This also will be lag, right? My bad. This also will be lag. Everything will be lag. Okay. Okay, let just hold on one second. Everything will be lag actually here. Okay, this also will be lag. This also will be lag. Okay, this also will be lag. This also will be lag. And one more thing, this last one, right? Last one will be lead, or for all of the cases, the last one will be lead actually. One second. Okay, so yeah, it will be okay. Again I missed this main point for which I did not copy it here, right? This should be here. Yeah, so this will be lag, option C. Okay, now yeah, let's do the third one, the angle between the excitation MMF and the resultant. So excitation MMF basically it is talking about the air gap excitation mmf, that is here. Resultant mmf is here. What is the angle between these two? That is what they are asking. So how will I find the angle between these two? So I know this angle, right? uh, okay, I know I have to find out the angle between these two. How will I find out the angle between these two? So this much angle is 90, that is for certain. And what is this much angle? So this much angle is 90 minus xi. This is psi. Okay, this is 90, right? So this is xi 90. Okay, so this much angle will be 90 minus xi, right? This much angle is 90 minus xi, and this is 90. So again the same thing, it will be this angle. So for the third one, I can just copy the picture of the first one. That this much angle is 90 minus I already cleared, right? This angle is 90 fr, and this. So what will be this angle? So basically again theta x plus this is my theta x plus this angle plus this theta, right, will be totally 90, right? This much angle plus this much angle plus theta will be totally 90. So theta x plus 90 minus I plus theta will be totally 90 degree, right? So 90 90 will get cancelled. Okay, so my theta x will be basically equals to xi minus theta. And what is xi? Xi is equals to theta plus delta, right? It is theta plus delta. So okay, it is basically the angle will be simple delta, right? The phase difference will be simply delta. What are they exactly asking? The angle between excitation mmf. Okay, a bit of mistake has happened again. Sorry for it. Okay, this will be delta only, but actually they are not asking that. They are actually asking the angle between emf. Again, sorry for the typo. I am really sorry. Okay, this will be emf. Okay, sorry, whenever just normal excitation is written, it should be emf. I'm really sorry. Okay, and this also should be emf. Okay, my bad. Okay, anyways, you are solving more questions, that's good for you. Okay, don't take it as a bad point, take it as a good point. So angle between the excitation emf and the resultant mmf. So excitation emf is here. Okay, this is my ef, and the resultant mmf is here. So this much is 90 and this much is delta, so it will be basically 90 plus delta. So angle between ef and the fr will be 90 plus delta. Now what is leading and what is lagging? So fr is leading ef, right? So, or other way around I can say it is lagging uh, it is lagging the uh, sorry, the excitation emf. Excitation emf lags the resultant mmf. Excitation emf lags the resultant mmf. So it will be 90 plus delta. 90 plus delta. Option B will be correct. Okay, so before solving the fourth one, I want to mention very quick thing here. So whenever there is a term known as air gap mmf, air gap emf, it is actually they are talking about er. Okay, and if it is talking about excitation emf, then they are talking about ef. Okay, and here also actually the wordings here are not proper. This, right, air gap, it should be air gap excitation mmf. Okay, otherwise you cannot understand what kind of mmf they are talking about. Are they talking about the field mmf or the resultant mmf? Okay, so whenever excitation will be there, you will describe it with field. If just air gap is there or resultant is there, right, resultant is written, then you will relate that with er. Okay, so yeah, that is the important thing over here. Okay, the angle by which air gap excitation mmf and the air gap, sorry, uh, sorry, this is air gap, sorry, this should be, sorry, air gap resultant mmf, sorry, not excitation, sorry, air gap resultant MMF. This we have already done now. Resultant MMF. Oh no, this we have not done. Okay, it should actually be resultant MMF. That's their typo. Okay, resultant MMF and the field EMF. Okay, okay, that is already done. Sorry. So this, right, this is wrong actually. This should not be air gap resultant EMF. Actually, this question, right, from where I took a bit of things are wrong there. This should be air gap resultant. And this should be air gap excitation. Okay, my bad. Otherwise, understanding it would be very difficult. So, air gap excitation MMF and the resultant EMF. Okay, let's solve the fourth one. So, if I see here, I have to find out the resultant EMF angle and the air gap excitation MMF, that is FF. So, FF is somewhere around here, ER is somewhere around here. So, this whole angle is 90. This whole angle is 90. So, if I just subtract this much angle, right, I will be able to find out the angle between FF and ER. What is this angle? So, this angle is 90. This angle is 90, right? And okay, this is delta, right? This angle is simple delta. The angle between the FR and FF is delta, right? Because the angle between ER and EF is also delta. So, both of them will just are shifted by 90. So, their angle also will be delta. So, this much angle is delta and this whole angle is 90. So, how much will be this angle? 90 minus delta. So, FF leads ER by 90 minus delta. So, it will be leads ER by 90 minus delta, that is present in option D. Okay, so that's about it for this question. Now the homework for you is do the same for a lagging load. If it's a lagging load, please draw the phasor diagram and solve 1, 2, 3, 4. Okay, 3 and 4, and tell me what are the answers, okay, of 1, 2, 3, 4. So this will be the answer of the questions, and that's it for this lecture. I will see you in the next lecture. Until then, happy learning.